In this video, I want to take a look at a second and, in my opinion, considerably more tedious method of finding particular solutions to our constant coefficient differential equations. And this one actually works on non-constant coefficient problems as well, as long as they're linear. But it, as you'll see, requires quite a bit more work and is, in my opinion, less intuitive than the previous approach. But let me go into it here. We'll talk about why it exists, why we need this method in addition to the other one. But for the most part, this should be sort of a backup method as opposed to the method of undetermined coefficients. So I want to go way back to earlier in the semester where we were looking at basically linear equations, linear first-order differential equations. So recall the linear first-order ODEs, where we had basically the integrating factor approach. So we had an equation that looked like this. We had dy dx plus p of x times y equals sum f of x. And we would use an integrating factor that looks like mu of x, and this integrating factor was e to the integral of whatever that p of x was times dx. And this is what we would use for our integrating factor. It would lead us to something that looked like the following. So this gave, after we found this integrating factor and multiplied everything through, we basically on the left-hand side would wind up with something that looked like e to the integral of p of x dx times our y, and it was a derivative of this basically, and you could product rule this out and it would expand to look like this left-hand side times the integrating factor. And on the right-hand side, we would have the same integrating factor, e to the integral of p of x dx times our f of x. And at this point, we would integrate both sides with respect to x. And on the left-hand side, the integral would cancel the derivative, and we'd be left with our e to the integral of p of x dx times the y. And on the right, we just have this big hideous expression that I can't really simplify anymore, but e to the integral of p of x dx times f of x would be some function. And we would always wind up with a plus some constant, just make it explicit. We would get a constant of integration. And then finally, we would solve for y by multiplying both sides by e to the negative of this power to cancel it out over here, and we would wind up with an expression that looks like the following. So we'd have a constant times e to the negative integral p of x dx. So basically e to the negative this times the constant, and then e to the negative this times the rest of this thing. So e to the negative integral of p of x dx times the integral of e to the integral of p of x dx times the f of x dx. Okay, so I know this is done kind of hypothetically and generically and hideously without any simplification, but this was the process. If you boiled down the process of using integrating factor. So this is our integrating factor. This is essentially what we did. We just simplified along the way so that we weren't carrying around integrals of e to the integrals everywhere. But this was the process. So if you go back and study this carefully, this is exactly what we were doing. So it turned out that in this case, if we were to try to solve the associated homogeneous equation, so the associated homogeneous equation. Right, so we're doing a first order equation. Here was the non-homogeneous one, right? We had this f of x over here, but otherwise this basically looks like a y prime plus something times y. It's just a first order version of what we've been looking at, but it's non-homogeneous because it has this f of x over here. But if we looked at the associated homogeneous equation, it would be this same equation, but without this f of x term. So it would be, so if I call this equation, equation 1, if we had the associated homogeneous one, which looks the same, dy dx plus p of x times y, but now it's equal to 0, this equation is solved similarly. So this equation is solved similarly. So basically, imagine we're doing the exact same thing. We went through all of these, so we'd find the same integrating factor. This is what the integrating factor would be. We'd group the left-hand side, it'd look like this. But on the right-hand side, when we integrated, instead of having this big ugly term, all we would have is a 0. And when we integrated the 0, we would just get the constant term. So we would just get the plus c term. Essentially, you'd go through the same process, but we'd only wind up with this term here, not this term here. Because essentially, you can think of the f of x, set f of x equal to 0, and suddenly this whole term goes away. So let me just jump to the chase here. So y equals just c1 e to the negative integral of p of x dx. Okay. So looking at this, I want to relate it to the stuff that we're doing now, where we're separately dealing with a homogeneous solution and a particular solution. And if we look at the way that we treated these first-order differential equations, we can now draw a parallel. Here was the homogeneous equation, and here was the homogeneous solution. Here was the equation of the full thing that had this part plus this part, meaning this, which matches this is the homogeneous solution, which must mean that this part, which is associated with the right-hand side, this must be the particular solution. So we can see that the solution has two parts. We have the homogeneous solution, which is the one that we just found here for equation 2. It looks like c1 e to the negative integral of p of x dx. And then we had the particular solution, which looks like this other big hideous part here. It's the e to the negative integral of p of x dx times the integral of e to the integral of positive p of x dx times the f of x dx. This big hideous piece here. So this is the homogeneous solution. And this is the particular solution. So the point of doing this isn't just to rehash a bunch of horrible algebra and write a bunch of horrible looking symbols, but to recognize that if we can do this for a first order differential equation, and we can successfully go back and in retrospect see that we've broken up the homogeneous and here the particular solution, then maybe there's a way to kind of extend this to when we're doing higher order ones. So what is another way to get this particular solution? So if this is what we're calling the particular solution, is there another approach that can be extended to higher order differential equations? That is the question. Is there another approach to find the y particular that extends to higher order ODEs? So now that we've identified what it looks like, that this is the particular solution, let's try to find another way to get this. And so again, this is a question, is there a way to do it? The answer is yes. Let me show you another way to do it. And that other way to do it can then be extended to higher order differential equations. So it's going to be similar in some ways to what we did when we did the reduction of order. Basically, we're going to say, if we know, comparing how these two pieces are related here, where we go. If I look at this, if I compare the, where do I have them? Here they are. The homogeneous and the particular solution. Notice that they both have this piece. They both have an e to the negative integral of p of x dx. It's sitting right here, and it's sitting right here. That means that the particular solution is basically the result of taking the homogeneous solution and then multiplying by some other big hideous function. And so I just want to take this as motivation. This piece is exactly the same as the homogeneous solution, and this piece is just some other big hideous function. So we see that yp is really constructed from basically taking y homogeneous and then multiplying it by this big other function, which I don't know what we want to call it. We can call it, I don't know, u. Let's call it u. So y homogeneous of x times u of x, right? So basically this piece here matched this piece here. That's what I'm calling this piece here. And this big old mess here, that's what I'm calling this piece here. So all I'm suggesting is, hey, we've noticed hopefully that the particular solution is basically written as the product of the homogeneous solution times some other function. Let's just say artificially, let's introduce this variable and say, let's call this the other function. And let's assume that our particular solution in these higher order equations takes a similar form to the form that it took here. So let's just assume that this is the case. So in this case, let's multiply and actually see what happens, basically, if we were to try to go back and plug this into the first differential equation. So we would need yp prime. To get the derivative of this, we would need to do product rule here. So first times the derivative of the second, so we'd have the y homogeneous times the u prime of x, plus the second times the derivative of the first, so that would be the y homogeneous prime times the u of x itself. And I'm suggesting basically that we're going to go back and plug into the ODE. So basically we're taking a guess for the form of the particular solution, and then we're going to go back and plug it into equation 1 here. So when I say the ODE, I specifically mean the non-homogeneous version. Okay, so I'm going to go plug that in. Let's get it all on the screen, hopefully, so we can maybe see this at once. So it's the derivative plus p of x times the function itself equals f of x. So here's the derivative. It's going to be y homogeneous times u prime of x plus y homogeneous prime of x times u of x. Right, so there's that derivative term plus p of x times y itself, which takes the form y homogeneous of x times u of x. And this whole thing should be equal to our f of x. So all I've done is, again, take this guess and plug it in to the original differential equation. Okay, so let's again kind of collect and see if we can rearrange some terms here. Notice in this case that we've got right here a p of x times our y homogeneous times u. And over here we have some other stuff times the u. So I want to kind of rearrange and regroup some of these terms together a little bit. So let's do that. So I want to group the terms basically in the following way. Let's do the u of x terms. So basically this term and this term grouped together. So I've factored the u of x out, and I'm going to be left with just the y terms. So I'm going to have, in this case, y homogeneous prime plus p of x times y homogeneous. So here's this term comes here, and these two terms together come right here. And they both have the u of x, which got pulled out. And that means this is the odd man out. That's the term I haven't touched. So we have this plus y homogeneous times u prime of x. And this whole thing is supposed to be equal to f of x. So why was that helpful? Well, you'll notice over here I have y homogeneous prime plus p of x times y homogeneous. I have plugged in the homogeneous solution to the left-hand side of the equation, which is the same as plugging into the left-hand side of this equation. What happens when I plug in y homogeneous into the equation of this form? Well, it satisfies the homogeneous version of the equation, which means when I plug in yh on the left side here, I do in fact get 0. So the whole point of this is that by plugging in, this is 0. And I can eliminate that entire term. So we have a much simpler expression than we thought. We really have y homogeneous of x times u prime of x equals f of x. And our goal is to figure out what does this function u look like. So let's try to solve for the u term. So basically, it's going to become essentially a differential equation here for u. So, solve for u of x. Right now it's u prime, but it's going to be a separable differential equation here. So let's write it all the way up. What you can think of this as being basically y homogeneous, which is again a function of x. U prime of x is going to be du dx, and that's equal to f of x. So I'm going to basically divide by the yh term, multiply by dx, and that'll leave the du by itself on the left-hand side. So I'm going to have du on the left, and on the right I'm going to have f of x over yh of x times dx. And we will integrate both sides, and what we'll wind up with is that u is equal to this integral, which for now I can't touch because I'm not picking a specific f of x or a specific yh of x. But that's what this u needs to look like. This means the particular solution, now that I know what u looks like, is the following. So let's just check. The particular solution, we said, is right here. Here was the substitution that we make. We just take the original homogeneous equation and multiply by u of x. Well, here's the u of x that we just solved for. So the particular solution is going to be y homogeneous times this. So y particular is y homogeneous of x times the integral of f of x over y homogeneous of x dx. That's what it winds up looking like. But, so right now, this particular solution that we just found here looks a little bit different than, where is it? This particular solution that we were trying to get it to be equal to. But let's keep in mind what the y homogeneous looks like. So essentially we were trying to find another way to get to that same solution. It doesn't look like it yet, but keep in mind what yh looks like. Our y homogeneous is equal to e to the negative integral of p of x dx, right? This is, again, come back up here. It takes this particular form. I'm just leaving off the constant. That's all I'm doing. So assuming that that constant is gone, I'm plugging this in for our yh into this general form that we have down here. So what is y particular then? Well, y particular is going to be yh, which is e to the negative integral of p of x dx times the integral of f of x over this thing. But what is 1 over this thing? Instead of having e to the negative power, you would just think of that as e to the positive version of that same power, right? E to the positive p of x dx. That's the same as 1 over y of h, which is what we've got here, 1 over y of h, times my f of x dx. And how does this compare to this, which I will erase this box in a minute so that we can actually read this. But how do those two things compare? They are exactly the same, right? e to the negative p of x, or e to the negative integral of p of x, e to the negative integral of p of x, a big integral of e to the positive integral, big integral of e to the positive integral, with an f of x, f of x. So they match, and we found a second way to get to the same particular solution, but this one doesn't require us using integration factor. So this was just saying, hey, let's make an assumption about the form of that y particular takes, that it takes the form of the homogeneous solution times some other function. And that was enough to go through and actually find out what form that other function must take. So we now have a second approach to get the particular solution, and this second approach will work on higher order differential equations. So this second approach works on higher order ODEs. Okay, so that's all we need to do. In this case, let's assume, so how would we do this? Let's try, in this case, that our y particular is going to take the form of some u times some already found homogeneous part of the solution. So basically, maybe it's some, what I'll call u1 of x times the first part of the homogeneous solution, which we used to call y1. And some other function u2 of x times y2. So basically, the idea is that where y1 and y2, in this case, are the solutions, let's just write this, that make up y homogeneous. We can write this, y homogeneous. Right, so basically the homogeneous solution is always c1y1 plus c2y2. We're using the same idea now, saying, okay, y1 and y2 are the parts that make up the homogeneous solution. Maybe the particular solution is just some other function times each of those individually. So that's all we're doing. If this is the case, let's take the derivative. And we're going to have to do a bunch of ugly product rules. So it's going to be, I'm going to drop the dependencies on the x's here. We'll just know that all these functions are functions of x. So it's going to be first times the derivative of the second plus the second times the derivative of the first. So here's first times the derivative of the second, first, second. And the second times the derivative of the first, second, first. Do the same thing for the other one. So it's going to be u2 y2 prime plus u2 prime y2. So there's what the second derivative, or sorry, the first derivative looks like. The second derivative is going to be the derivative of this. So we'll have the first times the derivative of the second plus the second times the derivative of the first. So just to be clear, I've done that part. That went to both of these. Now let's do the derivative of this piece. We'll get the first times the derivative of the second plus the second times the derivative of the first. And so this piece here goes to this piece here, and so on and so forth. So let me knock out these last ones as well. So we'll have the first times the derivative of the second plus the second times the derivative of the first. Do green and green. And then lastly, this last piece is, again, first times the derivative of the second plus second times the derivative of the first. So here is our giant mess of a solution. That is a very thick line. Okay, hopefully that's clear which ones match up with which. Whew. Okay, so what happens now? We need to plug these back into the original differential equation. So it's a big mess and a lot of algebra. plug into the ODE. And the ODE in this case is going to take the form of basically, let's call it y. So the equation is y double prime plus p of x y prime plus q of x y equals f of x. So this is the ODE that we're dealing with. It's a second order linear differential equation that's non-homogeneous, and we've divided through by the leading coefficient so that to make sure that the leading coefficient is a 1. So that is the idea. And now I'm plugging all of these in as the particular solution to this differential equation. So the first term is going to be the y double prime term. That's going to be all of this mess. So we're going to get a bunch of algebra. So just bear with me here. u1, y1 double prime. I'm going to group this term and this term together. We have two of them. I guess it doesn't matter. We can maybe come back and do that in a minute. It doesn't totally matter. But let's see how this. Now let's keep everything separate for now. This will just have to work. Okay. So let's plug in and see what we get from all of this. When we plug in the y particular, we're going to get that basically y particular double prime plus p of x times y particular prime plus q of x times y particular equals f of x. That's our hope. And in fact, instead of writing this here, let's see what we actually get. Let me start writing these in. So let me try to wise up and be a little bit smart about how I do this so that we can kind of try to eliminate some stuff. I want to group, remember we had a term here that we were able to kill off by basically putting in some terms that looked exactly like the homogeneous solution. So I want to do the same thing here. Let me group the terms, which is going to be basically all these y1 prime terms, all these terms that are proportional to the u1. So like this term, and this term, and this term. Let me group those ones all together, and then we'll do the same thing for the y2s, this term, and this term. So we get yp double prime. That's going to be basically a u1 times this term, y1 double prime. So I've taken care of this term. Plus p of x times y1 prime. That's going to be this term that I've taken care of, that I've factored again the u1 out. And we've just plugged it in here, so this part of this term, plus q of x times y1 itself. And that's going to be this term up here when I plug this one in. So I've taken care of this term, and this term being plugged in respectively to part of this, and part of this. Plus the u2 equivalent version of this, which is going to be y2 double prime plus p of x y2, come on now, p of x y2 prime plus q of x y2. So that is this term, and this term have now been taken care of, plugged into this differential equation with the appropriate in this location, and this location. These both go to 0 because by definition, y1 is a solution to the homogeneous version of the differential equation, and y2 is a solution to the homogeneous version of the differential equation. So that combination of the terms that have been accounted for so far gives us 0. So now we need to account for all of these remaining terms. So I'm going to do this one and this one. Let's write those ones down here real quick. So it's going to be y1 u1 double prime plus, what else do we have? y1 prime, u1 prime. Good, so that's that one and that one. Actually, let's just write them all out here. Plus, we had another version of that, so another y1 prime, u1 prime, and I'm keeping them separate for now, so that's that one for a reason. Do the same thing over here. We had y2, u2 double prime plus y2 prime, u2 prime plus another y2 prime, u2 prime. So that takes care of all of these. So we just wrote all of those down again. Those are the remaining pieces. Plus, we've still got this piece right here and this piece right here, which are both going to be multiplied if we come back down to here. They're both being multiplied by the p of x that we have because they both show up in the y prime term. So plus our p of x times both of those terms. So it's, what is it? y1 u1 prime plus y2 u2 prime. I think I got them all. Okay. So we've accounted now for every single term. So I grouped those first set here, they went to 0. I kept the remaining of the 6 remaining terms from here, they're written here, the ones that didn't get contribute here and here. And then the last two pieces were these two right here, which have been accounted for right here. They were in the yp prime term, right? Yp prime, which had to be multiplied by the p of x. So that's where this p of x came from. Okay, so there's everything. Let's continue to kind of group some terms. So what is this equivalent to? So again, this first line is gone, it's zeroed out. But if I look at this and this, just this grouping, so if I kind of group these ones together, and if I group these ones together, they look like the result of product rule. So this one looks like the result of d dx of, let's see, a y1 and a u1 prime, right? We'd have first times the derivative of the second. Here's the first times the derivative of the second, plus second times the derivative of the first. Second times the derivative of the first would be this term. So that's what that one looks like. Plus, let's do the same for the other one, d dx of y2 u2 prime. So that takes care of basically these two guys now. We've got these other two little pieces here and here that I haven't taken care of, so let me write those down real quick. y1 prime, u1 prime, plus y2 prime, u2 prime. And then we've got this big p of x term that I will also write out here. So plus p of x times y1 u1 prime plus y2 u2 prime. Okay, so there's that line. Let's group things up one last time. I'm going to group these derivatives together because we're taking the derivative with respect to x of this and this. Let's group that into one big term. So d dx of the y1 u1 prime plus y2 u2 prime. So there's those two terms. Let's do the p of x term now. P of x times y1 u1 prime plus y2 u2 prime, plus those last two terms that are sitting kind of by themselves. We'll just throw them in some parentheses here, but we're not worried about them yet. Now we've accounted for all of these terms. Why did we write things out this way? The whole point is that this whole thing is now supposed to be equal to our f of x. And our goal is to try to, again, solve for the u values. Our goal is to figure out what u is. And right now, you'll notice that basically we have all these u primes everywhere in here. If we try to basically force some things and just cross our fingers and hope for the best, we might get lucky. So what I want to do is basically force this piece right here, so the y1 u1 prime, where is it? Right here. The y1 u1 prime plus the y2 u2 prime. It shows up right here, and it also shows up right here. So we've got it in two locations. I've got it here, and I've got it here. If y1 u1 prime plus y2 u2 prime, if we can force that equal to 0, then our equation simplifies dramatically, right? This is really the only piece that we're going to have that winds up actually kind of surviving. We get two equations out of this. Okay, the first equation is the one that we just forced. So let's force this to be true. That can be one of our equations. So equation 1 will be the one that we just forced. Let's just say, right, the whole point is basically we have a huge mess of stuff here. We're really only trying to solve for two things, u1 and u2, but we have a ton of stuff here. So let's just, we basically have too few variables, trying to have, like, there's too much open-endedness. We can force some additional restrictions on this, and that's essentially what we're doing here. Okay, so I'm going to force that to be 0, and if that's 0, it forces the second piece. So if this is 0, and this is 0, and this is all gone, then it must mean that this equals f of x. So y1 prime u1 prime plus y2 prime u2 prime equals f of x. Okay, and now we have this big mess. It's a system of two equations, and ultimately we have two unknowns, u1 and u2. So I can rewrite this if you're, again, familiar with linear algebra. And if not, then don't worry about this. We're going to eventually just get to a formula at the end of all of this that looks like the following. Basically, we're going to use matrix notation. I'll briefly describe what I mean by this, but basically I'm going to have a u1 prime here, a u2 prime here. We're going to have y1, y2, y1 prime, y2 prime, and here we have a 0, and here we have f of x. And the way that matrix multiplication works is this equation is meant to exactly represent these two equations that we have here. When we do matrix multiplication, so a matrix is basically just a block that we write like this with a bunch of scalar entries within it. These are functions. They're just they represent a single number. But you multiply across on the one whatever's to the left and then vertically here. So basically I would go this way here, and that matches with going this way here. So the y1 hits the u1 prime, and then the y2 hits the u2 prime, and you add those entries together. And that's what gives us this result right here. So the top row times this column, basically kind of pointwise, you can think of it as almost, think of this as a vector, and we're taking the dot product of this vector and this vector. So this times this plus this times this should equal this. And that's the equation that we've got up here. And then the second equation is this times this and this times this. So again, across here, vertically here. So y1 prime times u1 prime, y1 prime times u1 prime, plus y2 prime times u2 prime, y2 prime times u2 prime. It's equal to the f of x. So across here, down here, and that gives us the top entry. And then you go across here and down here, and that gives us the bottom entry. So basically, to be totally clear, if we had a, b, c, d, I was multiplying by x, y, what this represents is basically ax plus by as the top entry, and then for the bottom entry it would be cx plus dy across, vertically here. So the a hits the x, the b hits the y, and we sum them together. And that gives us our top entry. And then we do the same thing for the second row here in the column. So c hits the x, d hits the y, cx, dy, and that gives us our second entry. And we get a another vector out of that. So that's kind of the process of how you do matrix multiplication, if you've never seen it before. And that's what this is meant to represent. So basically, we've got this big, ugly matrix. We can try to solve this. So we can solve with some linear algebra. Something called Cramer's rule. And it basically leads us to the following. So I'll skip all of this because, again, linear algebra is not a prerequisite, but let's get us as close as we can. U1 prime is going to be equal to negative y2 times the f of x term over this thing that's called the Wronskian. And u2 prime is equal to y1 times f of x over the Wronskian, where again, the Wronskian is just the determinant of the original matrix that we have sitting over here. So y1, y2, y1 prime, y2 prime. And remember, the determinant is basically this times this minus this times this. So you go this way and this way. This is positive, this is negative, and you add them together. So this gives us an expression for the u1 prime and u2 prime, which implies if we integrate to solve for u1, u1 will be equal to negative the integral of y2 f of x over w dx. u2 is equal to the integral of positive y1 f of x over w dx. And the particular solution y particular, which you'll recall was y homogeneous, in this case, go way back to where this all came from. Our horrible assumption way back at the beginning, right here. Y particular is u1 times y1 plus u2 times y2. Well, now we've found u1 and y1, u1 and u2, and it's u1 y1 plus u2 y2. So in this case, it's going to be negative y1 times the integral of y2 f of x over w dx plus the other one is y2 times the integral of y1 f of x over w dx. And this, after all of that work, is really just a formula to memorize. Okay, so again, if you've never taken linear algebra, most of this won't make any sense, especially all this stuff down here. But this is ultimately what we needed out of all of this. This is the formula. So I will encourage you to, again, watch through this because it's kind of nice to see the idea from where this comes. But ultimately, a lot of this math is kind of a level beyond where we're at. So let's just show how we can actually use this formula. In practice, we only care about the formula. And it's an ugly formula. And it's probably a formula that I'll think about it. I may likely even just provide this formula on the exam if I expect you to use it, because it's not one, certainly not one that I have like committed to memory until I like teach this class and look at it a couple times and I can remember and put it all together. So this is not something that's like an important life-altering formula that you need for the rest of your life, but it's nice to know what it's called so you can look it up. Again, this formula is the formula for something called variation of parameters. So let's do an example and put this thing to use to see if we can find the particular solution of the following differential equation. Y double prime plus y prime minus 2y equals the natural log of x. Why am I doing this? Because the natural log of x was not one of the functions that we were able to use doing the undetermined coefficients method. So the method of undetermined coefficients. This was not on the list of functions. And it turns out this variation of parameters is important because it allows us, it works 100% of the time for any non-homogeneous function. It doesn't have to be from that class of functions that we looked at previously. So in this case, natural log, we couldn't do that with the method of undetermined coefficients, but we can do that with this big ugly formula. So first things first, we need to find the homogeneous solution. And so let's give a domain restriction. We're dealing with a natural log. Let's say we're dealing with only positive values of x. So first, to construct the particular solution, I need y1 and y2. y1 and y2 are the two homogeneous solutions. So find y1 and y2. So basically, our characteristic equation, so we'll have y double prime plus y prime minus 2y equals 0, which has a characteristic equation that looks like, we'll call it m squared plus m minus 2 equals 0. This is one that we can either, again, you can use the quadratic formula, but this is one that I think I can factor. I'm looking for two numbers that multiply to -2, add to +1. So I think this is going to be m plus 2, m minus 1 equals 0, which tells me that m is equal to -2 or +1. And so that tells me the solution for y homogeneous is that it's going to be equal to C1 times e to the x plus C2 e to the -2x, where we can call this y1, and this bad boy right here is y2. Those are the two solutions. Okay, so now that I have y1 and y2 for this formula, I have this and this. We know what f of x is. It's right here. It's the natural log term. The last piece we need is that Wronskian, which is the determinant of the matrix that we get by putting y1 and y2 in, as well as their derivatives. So the last piece we need is the Wronskian, which looks like, again, y1, y2 on top, y1 prime, y2 prime on the bottom. So for us, that's going to be e to the x, e to the -2x, and then the derivatives, which are e to the x and -2e to the -2x. And we multiply this times this, and this times this. This gets a positive sign, this gets a negative sign, and we add them together. So we're going to get e to the x times -2e to the -2x. And from that, we're going to subtract the e to the x times e to the -2x. And what do we get from that? So adding powers, e to the positive x, e to the -2x. When we add those powers, we're going to get a total of -1x. The product here is -2, so we're going to get -2e to the -x. And from that, we're going to subtract just 1e to the -x for a grand total of -3e to the -x. So there is our Wronskian. Putting it all together into our formula. And we're going to find that y particular, which let me just write down the formula. It is, hopefully, let's see if I get this right. -y1 times the integral of y2 f of x over the Wronskian dx plus y2 times the integral of y1 f of x over w dx. Let's see if I did indeed get it memorized. Where do we have it here? Oh boy, sure enough. Good job, me. Okay, so again, I'm not going to make you memorize this, but we're just plugging into this formula. We have all the pieces. Here's my Wronskian, here's my y1 and y2, and lastly, there's my f of x. So what does my formula look like? We're going to get -y1, so negative e to the x, times the integral of y2, which is e to the -2x, times f of x, which is the log of x, whole thing divided by the Wronskian, which we just found was -3e to the -x dx, plus y2, which is going to be e to the -2x, times the integral of y1, which is e to the positive x, times f of x, which is log of x, over the same Wronskian, -3e to the -x dx. Okay, so that's a little bit ugly. And we're going to have to like go in and try to clean it up a little bit at least. This is not a very nice one to deal with. Ooh, those integrals are going to kind of suck. Maybe we'll just leave it in integral form. I don't know if I want to go through this. You can plug it into Wolfram alpha, but let's see what we get. So I'm going to get negative e to the x, and here, when I simplify this, we can pull basically this negative 3 out in front. We'll have our integral of this dividing by e to the negative x is the same as multiplying by e to the positive x. So I should get an e to the negative x log of x dx for that term. Good. And for the other one, same thing, e to the negative 2x. Let me pull that negative 3 out. And in this case, e to the x dividing it by e to the negative x is going to give me an e to the 2x. Whoa. E to the 2x, natural log of x dx. And we'll just say whatever, good enough. I don't feel like trying these. It looks like it's going to be a very tedious integration by parts. I'm not even sure if that'll work. This may be something that we have to save for Wolfram alpha. I don't see a clear way to integrate these right off the top of my head that's going to be clean. Integration by parts, my only guess. But even that, I don't ever see actually simplifying. I think we'll get an infinite series for our solution there. So it won't be explicit. So basically use Wolfram alpha to get an approximation for what this function is. So maybe this was a bad example. I'm sure that's an unsatisfying conclusion. So let's try one more example, hopefully less unsatisfying. And then we'll call it a day. So let's try this one. Y double prime plus y equals, let's do cosine squared of x. So again, cosine squared, that's not one of the functions that we saw. We saw cosine of x and sine of x, but not cosine squared or higher powers of these things. So if we want to find the solution to this, what we're going to have to do first is find y homogeneous. Basically, we're looking at y double prime plus y equals 0. Again, the characteristic equation of that should be m squared plus 1 equals 0. We'll see that that means m is equal to plus or minus the square root of negative 1, so plus or minus I. We have purely imaginary results. Whenever it's purely imaginary, this tells me that y homogeneous is going to be purely sines and cosines. So C1 sine of x plus C2 cosine of x. Right. Again, the formula is basically, remember, it was e to the alpha x times C1 cosine of beta x plus C2 sine of beta x. And for us, this is basically I plus or minus times our beta term here. So the beta itself is just supposed to be a 1. The I is wrapped up. It's not part of the beta that shows up here. Okay, so for us, it means beta was 1. Boom, boom. Alpha was 0, so this whole thing became a 1, and we just had C1 cosine x plus C2 sine x, which is exactly what we've got here. So there's our solution. This is what we'll call y1. This is what we'll call y2. And we can now construct the rest of everything we need. So let's find that Wronskian. So find the Wronskian, which again, y1, y2, y1 prime, y2 prime. For us, that's going to be sine of x, cosine of x. The derivative of sine is cosine, and the derivative of cosine is negative sine. And when we do our multiplication, I'm going to get negative sine squared of x minus cosine squared of x, which simplifies to negative 1. So our Wronskian in this case is simply negative 1. Okay. So in this case, oh, there we go. So we get that our y particular, again, which is going to be negative y1 integral of y2 f of x over w plus y2 times the integral of y1 f of x over w. So what do we get? We get negative y1. y1 was sine. So negative sine of x times the integral of y2, which was cosine of x, times f of x, which was our right-hand side here, so cosine squared, over w, which was negative 1, dx, plus for the second one, we'll get cosine of x times the integral of y1, which is sine of x, times our f of x, cosine squared of x, also over negative 1 dx. I can pull the negative sign out. We'll have just a sine of x sitting out in front of here, and now I just need to integrate cosine cubed of x dx. And for the other one, we'll have a cosine sitting out in front. Let me switch the sign to a negative to account for this minus sign right here. So I'll have cosine of x times the integral of sine of x cosine squared of x dx. This one requires basically a Pythagorean identity to kind of break down, and then we'll do a u substitution. This one right here is already ready for a u substitution. So if we want to treat these two pieces separately, piece 1 and piece 2, let's take a look at them. So if we're working on piece 1, I just want the integral of cosine cubed of x. And we'll come back and worry about the sine of x in front of it in a minute. So for this one, I'm going to basically peel off the cosine squared and rewrite that as 1 minus sine squared. So we've got the integral of cosine of x times 1 minus sine squared of x dx. That's the same as the integral of distributing through cosine of x minus cosine x sine squared of x dx. Let's let u be equal to sine of x. That means that du is equal to cosine of x dx. So here's my cosine x dx, and this is my u that's being squared. So this first integral, which is just the integral of cosine, is going to be sine of x. But the second integral is going to be minus the integral of u squared du. So the u substitution I only did on this part. For this part, I just integrated it directly. The integral of cosine is sine. The integral of this piece over here, here's my u squared. Again, u is sine of x, and here's my dx, my du term. And so we get sine of x minus 1/3 u cubed. Forget about the plus c. We don't really need that term, which means this whole piece is going to be sine of x minus 1/3. U was sine, so sine cubed of x. Okay, so there's that piece. There's integral 1. Now let's do integral number 2, which is just ready for a u substitution right from the get-go. It's the integral of sine of x cosine squared of x dx. So again, let's let u in this case be cosine of x, meaning du is going to be the derivative of cosine, which is negative sine of x dx. I just need a negative sign here. We'll pull a negative out in front, put a negative there. And now this integral is going to be negative the integral of, I've got my u squared and my du, which is negative the integral of 1/3. Sorry, drop my integral. I've already evaluated it. So negative 1/3 of u cubed. And what was u? It was cosine, so cosine cubed of x. So put it all together. got our u substitutions. We found these two integrals. We just, again, need to compile the whole solution. Here's what the solution looks like. So it's sine of x times the result from this first integral. And here's the result from the first integral. So it's sine of x times all of this. Y particular is sine of x times sine of x minus 1/3 sine cubed of x plus, so we've taken care of the sine of x times this integral, and now it's going to be minus cosine of x times this, but this minus sign will cancel this minus sign to give us a plus, and we will just have a 1/3. We've got a cosine x here and a cosine cubed x here, so it's going to be a 1/3 whatever cosine x times a cosine cubed of x. And now we can kind of come in here and simplify the rest of the way. So what do we get? I see a sine squared of x minus 1/3 sine to the 4th of x plus 1/3 cosine to the 4th of x. So there's a big ugly mess. This can be simplified a little bit if we're willing to do some ugly algebra. I don't know how much time we need to waste, but basically I can play a little bit with these two terms. So we could write this as sine squared of x minus 1/3 of, or plus 1/3 if we want, times cosine to the 4th of x minus sine to the 4th of x. This can be thought of as the difference of two squares. So I could write this as, let's see, a cosine squared of x minus sine squared of x times a cosine squared of x plus sine squared of x. There's my difference of squares. But this piece right here is 1. So I can drop that part out entirely, and we have sine squared of x plus 1/3 of, now we've got a cosine squared of x minus a sine squared of x. We can do a little bit more grouping here if we're clever about how we do this. We've really got a sine squared of x plus a 1/3 cosine squared of x minus 1/3 of the sine squared of x. I can borrow a little bit from this guy to this guy to make it positive. Between the two of these, I really have a positive 2/3 sine squared. But let me break that up into a positive 1/3 sine squared of x plus another positive 1/3 sine squared of x. So again, that's this one plus this one gives me 2/3, and I've broken it up into two separate 1/3. Why? So I can group one of them with this cosine squared. What does that equal to? That is simply a 1/3. You could factor the 1/3 out and just get a sine squared plus cosine squared, which is 1. And when it's all said and done, we get a 1/3 times a 1 plus sine squared of x. So if we want, we can simplify it all the way down to that mess. As you can see, variation of parameters is not a particularly fun approach. Even when it works, it's incredibly tedious. And there are cases where you'll get something. I mean, this is the solution. It's just that this is not a nice analytic integral that we can perform. Doing integration by parts would lead to an infinite series for the solution of this thing, as far as I can tell at least. So, long story short, variation of parameters exists. Use it only as a backup. If your non-homogeneous part is a polynomial, a sine or a cosine, or an exponential, or any sum or product of those, use the method of undetermined coefficients. And only in the rare case that you wind up with something like this, a log of x, trig function to a higher power, then you have to use variation of parameters. And it's not always very much fun. So, good luck.